Hello, everybody. So we are going to talk about electrical diagrams today, specifically one-line diagrams, interpreting them, in other words, reading them. What does all that information actually mean, and how do you use them effectively? So we've got a lot to cover, and I'm going to show you some examples. Just a quick introduction. My name is Caitlyn Wininger. I'm a certified electrical safety compliance professional through NFPA or CESCP, and anyone who's in charge of or helping with electrical safety, I highly recommend you go check that out. It's a great certification to get at this time. I oversee the training programs and electrical safety trainings, audits, program writing, anything that Herzig Engineering offers. So if you need any help with that, of course, you can always ask. We are going to, of course, cover how to read a one-line diagram, as well as the requirements behind them. So they're wonderful tools, but there are some requirements to them. And I don't think everybody realizes that, yes, it is required to have it and update it so often and utilize that information for certain studies. So we'll cover that as well. And then just 3 short tips on how to improve your use of those kind of diagrams today. If anybody has questions, please feel free to use the question feature in GoToWebinar and submit that at any point during the presentation. I've got it pulled up and I'm able to watch for any coming in. If you have any comments as well, you can use that for interacting with me today. So I will be observing those as they come in. All right, so before we dive into introduction to reading electrical one-line diagrams and talking about what all information you should be able to find on them, I'm going to have a poll. Does your workplace have up-to-date diagrams, one-line or single-line diagrams? Yes. Yes and no. We have them, maybe not up-to-date. No, or not sure. So you go ahead and click the response that's applicable to you and click submit. And that'll give me an idea of where we're starting with as far as familiarity with this topic. Okay. Give it just a couple more seconds. All right. Okay, so most of you do have one-line diagrams and feel pretty confident they're up to date. And then a close second being you have them, but they might not be up to date. That's totally fair. And for those of you who aren't sure, you know, probably at some point you had system diagrams, but maybe got pushed off to the side and they're left in the bottom of a drawer in a maintenance desk somewhere. You know, it happens all the time. So getting those up to date or recreated is very helpful. All right, so let's go back to make sure the screen's shared. Okay, so how do we utilize those if you have them? Well, first off, we just have to understand what is it. Well, a single line diagram or a one-line diagram is exactly what it sounds like. It's a diagram of single lines, go figure, that show the elements of an electrical system and how they are connected together. In other words, it's a map of your electrical system, not necessarily where it's located in your facility, but more about how each thing is electrically connected. So what feeds what? Which breaker is going to turn off this motor? Which fuse disconnect is going to feed this panel? You know, things like that. And this is just an example. Not going to dive into it too close because later I'm going to pull up some sample drawings and zoom in and really talk through it. But this is just what we're talking about today. There's a lot of information on it, and it tells you where everything is connected to and from. So what kinds of things are included on that diagram? Well, it should be impedance elements, wires, cables, stuff like that. Energy sources, you know, your utility points, generators, protective devices, so breakers, fuses, relays, as well as some other elements. And let's dive into those specifics. There is a lot of information on these diagrams, typically. So for the wires and cables, typically we like to see that it has the size, the length, the number that are landed per phase, what material is being used. You know, copper is most common, but sometimes it's aluminum, for example. Is it raceway? Is it open air? You know, some specifics about what is that cable exactly. Not just, hey, this is connected to that, but how? What is the wire size? What is the length? Such and so forth. Some reactors or inductors for filters at drives, those could be included in the diagram as well. Transformers and their information. So not just the kVA and the voltages, but what's the percent impedance? That actually does make a difference. Is it step down? Is it isolation? Let's list all those details on the one-line diagram to make it as most useful as possible. For the energy sources, we're looking at the utility contributions. So the utility fault current, NVA contribution. What is the voltage? What's the X over R ratio? What's the three-phase or line to ground fault current availability? Motors and nameplate info. So motors can have an impact on various studies because of the backfeed of power into the system. So what is the voltage? What is the rating? Horsepower, maybe even power factor for medium voltage stuff. That can impact some of those studies, like I said. So getting that information detailed on the diagram can be very helpful. Same thing for generators and nameplate info. It's kind of similar information there. So voltage or kilowatt rating. Sometimes they have horsepower as well. There's a lot of ways that you can get that information. Some generators even have protective devices in them. And so you kind of create your own little system diagram for the generator as part of that. Any renewable sources are starting to get put on these single line diagrams as well. Most common, solar and wind. We see the PV systems more commonly than anything though, as far as what's included on a diagram. For your protective devices, we're going to look for things like high voltage or medium voltage relays. So not just what is the make and model, but what's the CT ratio? What are the adjustable settings for that? Fuses. You know, not just the size of the fuse, but what is the model? What is the make, the class of that fuse? And if there's multiple types, you know, sometimes over the course of keeping a facility maintained, you look and think, okay, I need a set of 200 amp fuses. Well, I've got 2 FRSR and 1 A60. Well, they're all 200 amps, so that's what's going to be put in there. Not the best idea, but it happens. Making sure that, well, whenever we see that, we list it and we make it very clear what actual fuses are in place. Breakers, same idea. So making sure that the make and frame is identified somehow on that drawing. Trip unit model, sensor, plug, what are the settings? What's the amperage rating? Detail all of that. Other elements could be UPS systems, you know, looking at the kW and voltages, VFDs, soft starts, DC drives, what are the ratings for those, the details for those. Okay, so there's a lot on there, but I think it's easiest if we just pull up some examples and work top to bottom, run through what this might look like. Okay, so I'm gonna pull this over here. It should work just fine. Okay, so this is an example of what one of our drawings might look like. So if we do a study or an analysis, this is the format that you could expect. We're going to zoom in here. Okay, so I've got a question about BESS. So I'm assuming that means battery energy storage systems. I'm trying to remember. I don't work with that quite as often, I'm going to be honest, but I do sometimes see those on there if that's what you're referring to. It's not super common yet that we see those in the field, but there are symbols for that if needed. All right, so zooming in here, hopefully everybody can see this. It starts out at whatever the utility source is. So it could be your company name. You know, local one for us would be Evergy, and looking at what contribution they have. The amount of available fault current depends on your location and where you're at on the grid. As we are connected on a grid, that available fault current can change over the course of time. Plants are put into service, taken out of service, and that affects what's available on the line. Okay, so some information that could be helpful, such as the meter number or the transformer number, just so that in the future reference, when you're asking for updated information, you can go ahead and look at it. Whether it's provided on the primary or the secondary side of your utility transformer also makes a big difference. So having those notes included is very helpful. Okay, so that's an example of what that utility contribution might look like. So this, for example, has short circuit contribution for a three-phase short circuit contribution of 33,900 amps on the secondary side of your transformer. So that's what you're looking at as far as your fault current. Okay, and then we've got 8 500 kc mil cables, meaning there are 8 wires landed on each phase for 40 feet before you get to your main switch gear. This is, again, just an example. And we run the calculations and you get the voltage information and the arc flash hazard analysis and boundaries and things like that. In that switchgear main, you can think of those solid lines as like an electrical enclosure. So that is where, you know, it's the physical piece of equipment, and what's below that on the diagram is what's inside that enclosure. So in the main section of the switchgear, you've got this fused main switch. Okay, and this is going to be a Goldschmidt A4BY, 3000 amp rating, 600 voltage, rating. More cables. This time it's only 1 cable per phase, 3000 kc mil, 10 feet. And what is the rating of that cable? All right, and then it goes into the rest of the switchgear. So everything under this horizontal line is considered switchgear 1. And there's multiple switches. Again, more fuses. That's what the little rectangle symbol is. That's a fuse. The squiggly lines here, that's a cable. That's an impedance element. And then you just continue following the map. So switchgear 1, switch 1 feeds a 500 kc mil cable, 1 per phase, for 350 feet until it reaches panel PF, whatever that means to you. Okay, with the voltage information. Now we're getting into breakers. So here we have a breaker, for example, a Siemens BQD, it could be square D, it could be GE, it could be a lot of things. The amperage rating, trip, plug, sometimes those are different. More cable information and some load information. Over here on the next one, we've got a transformer. So this is an example of what a transformer symbol might look like. So again, the size, 775 kVA. The primary is 480, and then it transforms down to 208 with a percent Z of 4.8. So the impedance of it is 4.8%. Okay, and that splits off to 2 different disconnects. More information for those. So those are some basic information items that you should look for. Sometimes we even just see there's a fuse and it's got a note that says spare. There's nothing connected to it yet. That's pretty common. Or breakers that are put in place but nothing's landed on it yet. Go ahead and model it and then just list it as spare so that people know, yes, okay, that doesn't actually feed anything yet. It's free to use if the case arises. Okay. Let's see if there's anything else relevant for the data. I think we covered it. Fuses, transformers. Okay. Another way of looking at these solid lines, so 6 pumps, disconnect switch, every one of these solid lines we would consider a label point. So that would get an arc flash label if that was part of the arc flash study, containing the information of the analysis results. Okay. Oh, here's another one. So this little switch looking thing, it's a disconnect switch that is not going to include any protective device. So it's just a knife style disconnect. It's not got any fused elements in it. It's just an isolation point. So no protection, just a place to turn things off. Versus the fuse, yes, that's a switch, but it actually has fuses in it. So there's an example of that. Over on the right, of course, the study information from who provided that study should be on there. And then there's a place for engineers to seal the drawings. So any engineering study should be signed off on by a licensed engineer. And so their seal and signature should be right there. We typically include a legend of the most common items you're going to see. So circuit breaker, fuse, wire, or conductor, transformer, the panel itself, or in the enclosure, which also could be called a labeling point. Sometimes there's a revision table. So, if it's created originally and then you've got changes, you can mark revisions, on this date, we changed out this for this, and mark up your drawing to make it real clear what has changed over the course of the years. Okay, and then some project information at the end, who did it, when was it done, project number for us internally, and the drawing name. So as you get familiar with your electrical one-line diagrams, you'll get to know, okay, what drawing do I need to go find? Well, hopefully it's easily named. So this one, switchgear 1. So stuff fed by switchgear 1 can typically be found on that drawing. And there's a continuation. Here's switchgear 2. So they have a whole separate utility source for this, for their second switchgear. Trying to find, oops. So there's also links. In other words, you know, this is a continuation. It was too big to fit on one drawing and still make it readable if you print it out, because it'll just shrink down and down and down because it's too much information. So if it's a continuation from another system, it's all part of one switchgear, for example, we'll have that noted. Oh, here we go. Here's a motor, for example. So this one was provided kilowatts instead of horsepower, but it's, you know, the motor size for air compressor 2 fed by switchgear 1, switch 20. It's a 200 amp little fuse JTD. Okay, so then that way, you know, okay, we've got a problem. The switch upstream of this motor, the fuses blew, you know, they operated, we need to replace them. Instead of necessarily having to go out and look at what's physically there or remember it, because sometimes people just pull the fuses knowing it's bad and then throw them away. You can always go back and look at the one-line diagram. Okay, what was there? What's supposed to be there? And another thing is, you know, we've got our one-line diagrams and something goes wrong and you go in and you look, well, that data doesn't match the diagram anymore. Maybe that's part of the reason there was a problem. Maybe it was the wrong type or size, or it was the wrong class of fuse that was put into place. And, you know, the inrush requirements for this motor weren't handled by that fuse style. There's a lot of things that you can start using these for, like troubleshooting and stuff like that. Okay. So if anybody has questions about the information on a one-line diagram, reading it, understanding how things are connected, please feel free to submit some questions here. So there's some questions about selecting information, like fault clearing times and things like that. That's more in the engineering analysis side of things. So once you have a diagram created, you would then go and perform that study and analysis to determine what exactly makes sense for your system. So the diagram is just the starting place, and then you use that information for various things. Okay, are there any other questions about reading a one-line diagram? The more information on there, the better, frankly, without getting too cluttered. Because I've seen some interesting one-line diagrams before where you're just like, oh, it's all jumbled up and, you know, things aren't spaced out well, and it's hard to follow. But we try really hard to keep it up to date. So Paul has a question. Does a full table of data accompany the PDF one-line diagrams? Yes, typically if it's part of a study, if we're building this as part of a study, we will run the calculations, and of course some information's on the diagram, but then there are relevant tables of data provided as well. So for example, the protective device information, all the breakers, their models, their settings, each individual setting for you know, instantaneous, long time delay, short time delay, all that stuff. Fuses, their models, their sizes, relays, same idea. All that information can be listed out in what we call the protective device settings report. Arc flash analysis results has its own report. Yes, there's a lot of detail that you can get once a diagram is compiled and created in a program such as SKM or Easy Power or something like that. And we typically use SKM, but that's a personal preference for a lot of our engineers after having tested several others. There's plenty of options out there, and we can work with whatever's needed. Okay, I'm going to go back to the slides. If there's any other questions, I can always pull up the example drawings again. Okay, so let's talk about utilization and update requirements. I briefly mentioned as I was walking through the different elements you might find some of the utilization, such as, you know, troubleshooting. Well, is this even the right installation design as we had originally decided to use, the fuse types, for example, or the breaker settings, because someone's messing with the breaker settings. That's a problem. So troubleshooting and actually trying to maintain your equipment and knowing what should be where is a big part of it, but there's more to it than that. So let's talk about it. So we've got 3 main codes and standards to follow. We have the NFPA 70, or the National Electrical Code. So that's the installation requirements. The reason why I'm bringing this up is because, well, with that installation requirements, the design of your equipment should be well thought out. And most of the time you end up with some system diagrams as part of that design process. Sometimes end up being as-built whenever you go to contract. Those are wonderful, wonderful starting points. Now, sometimes those get changed pretty rapidly during the process of construction or renovations. As materials are back ordered and they swap it out for something else that's similar but not quite the same. A lot of people think close enough. Well, maybe not. So let's go ahead and update that drawing because it's not the same, and you need to know that for future reference for any studies that are involved. So usually in that initial build or any renovations as part of the NEC, following that is making sure that you have your documentation in order. And then we've also have the NFPA 70B. It's a standard for electrical equipment maintenance. So let's say you've got something in place already. Now it's time to just keep it up and running. This is a fantastic tool to look at. However, it is not going to duplicate or supersede manufacturer instructions. In other words, if you're already following manufacturer requirements for electrical equipment maintenance, you're the majority of the way there to being compliant with the 70B. Now, it does fill in gaps, and if you don't already have a safety or a maintenance plan, then it can be the fantastic starting place for you. It's got wonderful forms and it lists out when each type of maintenance activity should occur based on the condition it's currently in and how to evaluate the condition it's in to determine those time intervals. I have a whole webinar about NFPA 70B that you can go back and watch on our YouTube channel, but it is a fantastic resource that you can use and is actually a standard now, so it's required to be referenced as part of your electrical maintenance. I bring that up because part of it is also talking about studies, making sure that if your equipment's maintained well, great. Is it still rated for the system? Is it still designed properly? Because things change over the course of many years. I don't know about you, but I don't live in a fairyland where every time equipment breaks down, you get to replace it with the exact same make, model, size, everything every time. So making sure that those studies stay up to date is a key element as well. And we'll look at some references on that in just a moment. And then we've got the NFPA 70E, which is the standard for electrical safety in the workplace. So this is the one that I spend most of my time in, and I can certainly answer any questions over this pretty confidently. The other two as well, I would just typically like to have the book on hand to reference a little more frequently. 70E, I think I got you. But it covers the types of studies that you need as well, more commonly referenced for the arc flash study, which having a single line diagram is one of the first steps to getting that study completed. You have to know all of that information that we're talking about, all those elements I walked through prior to and during looking at single line diagrams. That is all included in an arc flash study. So having that diagram makes it a lot easier to perform this analysis. Okay, so let's look at some specific uses of those single line diagrams. It's oftentimes used by engineers or some kind of engineering firm. We use power system software such as SKM, ETAP, Easy Power, and can analyze the system using that diagram for things such as arc flash, equipment AIC ratings, protective device coordination. We can do, of course, the short circuit calculations and have that information on the one-line diagram based on those utility contributions, motor backfeeds, generators, alternate sources. So each bus can be faulted to determine the voltage fault current available. Okay, and that's also going to be impacted by your impedance elements, such as your wires and your transformers. Even energy loss may be offset by motor backfeed. Okay, step-down transformers, that impedance that present C impacts the results as well. The voltage step down increases current. Again, every piece of information is important. So estimating or guessing, which is really what I want to call it, not always the best option because it can drastically impact the results of various studies, not just arc flash. But of course, that's one of the major ones we always talk about based on the IEEE 1584 2018 version for performing arc flash calculations. So understanding the arcing fault, current, and device operating times to then provide you the appropriate PPE recommendations. Okay, so three-phase, line-to-line faults. There's some parameters for that that are included in your diagram information as well. So that calculation provides the potential incident energy exposure, gives you some PPE, as well as the boundaries. So the boundaries oftentimes are also put on the one-line diagrams for reference. One of the main things when looking at engineering recommendations is about keeping your devices coordinated properly. Okay, so having an idea of where everything is in the system is essential for coordinating it properly. So just looking at data and physically where it's at is great, but seeing that diagram telling you, okay, this feeds this and this feeds this, which feeds 16 other things, well, you don't want one of those 16 things to trip the main. Okay, so being able to prioritize your coordination by seeing, which one would have the most impact versus least impact if it were to operate, as well as helping lower the arc flash hazards. Having one line diagram makes it easier to do the calculations and produce these kinds of labels too, which are required as well. So it can help with designing projects, understanding what do you have available, where do you have electrical room, I should say, in your system to support renovations or changes, looking at maintenance of equipment, double checking that you're still replacing stuff with the like equipment, not just similar, but the same equipment. And if it's not the same, mark it up. Make sure that it's noted that something's changed. It's great for troubleshooting, like I mentioned earlier. Lockout tagout's a big one. So understanding where things are fed from and if there's a chance for backfeeds or an automatic transfer switch or something like that, that really helps make sure that nothing goes overlooked whenever performing lockout tagout, energy source isolation verification. Okay, of course, arc flash hazard calculation and mitigation, determining AIC ratings. So is it even going to withstand a fault, or is there too much fault current going through it and it's going to blow up on you? That'd be good to know. Protected device coordination, such and so forth. So these diagrams are versatile, very useful, as long as they're kept up to date. So let's dive in a little bit closer to the NFPA 70B requirements for single line diagrams and systems studies. So they do need to be completed in accordance with applicable codes and standards, including the 70B. Single line diagrams shall be maintained in accordance with 6.2 right there. Up to date single line diagrams shall be the primary reference for system studies. In other words, like I've been saying, this is your starting place. It assists with so many various engineering studies or system studies that having a one-line diagram that is correct and accurate to what's physically there is a big deal. So maintain it in a legible condition. Some people print them out and hang them up on the wall. Fantastic. And then you handwrite updates. Make sure it's legible. Make sure you get that reprinted every now and then with those changes. Shall be kept accurate, shall indicate the date of the last revision. That's a pretty good clue because if something's changed since then, you look at the date of the last revision next time you're going to do troubleshooting or locking something out, and you can think, oh, nope, we've changed stuff since then. I'm going to have to do some circuit tracing and mark this up to make sure that my area hasn't been affected. When single line diagrams are not available, the facility or equipment owner shall be responsible for providing an equally effective means of obtaining the necessary information. And I can tell you that equally effective means later turns into a one-line diagram most of the time. So, you don't have one currently, well, you better start collecting the data, and then eventually that gets put into a diagram anyway. And whenever it comes to updating them, it mentioned keeping it accurate. Well, technically, it shall be reviewed for accuracy at intervals not to exceed 5 years. For all the studies and the diagram requirements, it is very clear. Intervals not to exceed 5 years, you quote unquote review it for accuracy. I'm going to take a little side note here. It says shall be reviewed for accuracy. I can tell you vast majority of the time, we might as well just say update at intervals not to exceed 5 years, because if you're waiting 5 years to get it reviewed for accuracy, I have a pretty good bet that it's going to need some changes. It's going to need to be updated. So that's going to impact your short circuit studies, coordination studies, load flow studies, reliability studies, arc flash studies, such and so forth. So when should they be updated? Well, every 5 years at a minimum, or when there's new installations or modified systems. That impacts the results of all those studies. There typically needs to be an annual data verification for generation and transmission. If there's a change in utility or source, so you have a different transformer, or you know that there's been an impact, you know, you've been refed from a different system. Changes system impedance, so different wires. Things are fed from a different location now. The configuration's different. You have maybe you had to increase the wire size because you were dealing with voltage drop issues. That's a change in the system. It changes the impedance, it changes the calculations, the configuration, the loading, how many motors are running, what are the sizes of those motors, what's fed where. Maybe you installed a VFD or a soft start because you're having trouble with it. Well, that impacts the results of the study. So make sure that those are also reviewed and updated as changes are made. Again, keeping that diagram up to date being the first step. How do you know if something's needing updated? Well, just compare it. Look at your single line diagram, look at your physical equipment, do an audit, a walkthrough of sorts. Okay, is switchgear 1 main still a circuit breaker and a fuse of these type with these settings, model, all of that? Yes or no? And then you mark it off as you go. You can do a review every now and then of that. Specifically, like I said, any renovations, anytime you're doing maintenance and you know something's changed, let's go ahead and get that reviewed and updated. So, question for you guys. How often does your electrical system have changes? Do you think it's not often? Do you understand that it's pretty much all the time because you end up just having to maintain and get equipment up and running with whatever you have on hand? Or are you pretty consistent with changing out, you know, breakers with the same type and model or fuses, and you're only really concerned about having to update this stuff whenever there's new equipment or you're doing major renovations and it's not changing like for like equipment? Okay, getting some responses in here. All right. Can definitely see a theme with the responses here, with the majority saying what I kind of expected. All right, I'm gonna go ahead and close out the poll here. So over those last few seconds, it kind of changed drastically. A lot of people ended up saying you're only worried about changes if there's new equipment or renovations. Fair. For a while, the by and large answer, which was the one I was expecting, was the second one, that you know it happens all the time. Stuff has changed. You end up replacing stuff with whatever you have on hand because you got to get it up and running. It happens. I get it. Having a whole bunch of spares in your maintenance shop of all those unique fuses and breakers and wire types and sizes and all that is sometimes kind of difficult. It's transformers, especially motors. If you can't replace it with the exact same thing that was there originally, though, that constitutes a need for an update. That's a change. It could be that you keep track of those and every so often you schedule a regular update to capture all those changes at once. Or it could be that you go ahead and every single time there's a change, you've got it ready to go, updated. You got a form or some kind of documentation system to make sure whoever's in charge of your diagrams gets your diagrams updated. Okay, got a couple questions here. So Thomas asked, how can a company that owns 200 plus buildings that haven't had one lines updated for a significant amount of time without original or modifying original one line reasonably perform the required updates? Fantastic question. So you have a lot of buildings and one lines that have not been updated for a long time. For us personally, we would just see that as, okay, it's great that you have diagrams and that can give us some information for your larger systems and give us an idea of what's there, but we'll more than likely recommend just go ahead and start from scratch. Maybe you can update them, but if it's been a significant amount of time, I can imagine that a lot of that information is not going to be helpful, and it's just going to confuse things more than anything. And so starting back and looking at the utility, looking at that incoming power, looking at those switch gears, writing it all down again and rebuild those diagrams. And it can be time consuming because without accurate current information, you really can't perform those studies, those updates, because the updates are supposed to include whatever has been changed. So unfortunately, there's not a real quick fix to that. It's going to take some time. It's going to take some investment of time and resources to get that information collected and then create a new one-line diagram or spend the time to update the ones you do have. And then we've got another question from Paul. This may have been mentioned earlier, but what are the standard changes that impact arc flash hazard analysis and require only 3-phase circuits above 60 amp breakers, 50 horsepower, 100 amp fuses? Are the standard changes that impact and require updates only? Typically, that's what we would go off of. I see what you're saying here. Yes, 3-phase circuits are typically what we're concerned about. By and large, single phase, I mean, it can arc, it can flash on you. I'm not going to say it's not hazardous, but there are no specific calculations for that. And it's been suggested that you use 3-phase calculations for single phase to be conservative. But there's been some research on that kind of justifies that it might be over conservative. So yeah, we're typically worried about 3-phase. And then there's this 60 amp rule mentioned, 60 amp breakers or 100 amp fuses, 50 horsepower. That is just based on our experience. So there's nothing necessarily that specifies those cutoffs, but based on our experience doing thousands of studies, there's a certain threshold after it's gone through a certain number of system protective devices. And if nothing's changed, there's no transformer, there's no large motors, there's no extra components that will then impact the results of the study further down to make it higher hazard. Yeah, typically we're not worried about updating those low hazard points. We still look at them, we still verify them, but you don't end up necessarily having a different hazard result unless you're putting in a transformer or a different motor, a larger motor, or if you're having to refeed equipment and it's a super long run now between the protective device and the equipment, because that can have extra impedance and cause the breaker to trip slower, and so maybe it actually does need to have its specific calculation and update. There's a lot of factors to it, and I feel like I'm talking in circles, but I hope that helps get you on the right track if I answered the question the way that I read it. If there are any other questions, comments, or if someone wants to follow up, maybe I didn't quite get your question answered the way you were hoping, please feel free to clarify or submit a new question. Okay. All right, so how do we actually use these? Well, I've talked about it quite a bit, but realistically, the actual tips to implement it in your workplace. Okay, good. We've got, well, create and update those one-line diagrams. If you have not had a diagram for your facility, or if it's been since it was originally built, back in the 90s, 80s, it's gonna probably just need to be recreated, all right? But if it's been more recent, if it's a newer build or you have been keeping up to date with those diagrams over the years, just go back and review it and get it updated now. Start fresh if you haven't within, the last month or so. Make diagrams accessible. Here is a big, I don't want to say pet peeve, but kind of mine. If you have one-line diagrams, but it's in someone's personal folder on their computer, or they have one copy that's in a folder at a manager's desk, and nobody really knows where they are or when to access them, or it's a process to try to get their hands on them to look at them, that's not helping anybody. All right, make them accessible. Maybe you don't want everybody editing them. Maybe you don't want everybody marking them up. That's totally fine. There are ways around it. So the online shared stuff, you can lock documents. You can make it, accessible for viewing only, and they're not allowed to make edits. That is possible. Same thing for physical copies. All right, print them out and laminate them. Makes it a little harder to mark on. And if they do, well, you can just get some rubbing alcohol and wipe it off if you don't trust their marks, and you go verify it yourself. That's fine too, right? Somehow, some way though, you should make it accessible and be open to knowing when there's a change. So, again, maybe you don't want everybody changing stuff on those diagrams that everybody's referencing, but somebody does need to be in charge of that and listen whenever those concerns are brought up. Hey, this doesn't actually feed that motor anymore. Okay, don't just say, I'll check on it later. They're bringing it to your attention now, so either mark it down or go check it now. There's a lot of times that changes are talked about, but the person who's in charge of updating it never gets around to actually doing it. All right, so make it accessible, make it up to date. And schedule regular updates. If you don't have a good way of keeping track of every change, which is really the best practice, every time there's a change, go ahead and get it updated, go ahead and get it revised, at least marked up for a future revision. But go ahead and schedule those regular updates. Put it on the maintenance calendar. Minimum every 5 years. I'd say go through and do a walkthrough every year, every 6 months even, and check off things, especially areas that things have been worked on. And if you haven't gotten updates and changes listed from the workers, go double check it, right? Every 6 months to a year. That way you're not working out of date for too long. The more often you can update it, the better for everybody involved. All right, and if you don't know where to start, if this seems like a pretty big task, we definitely got you covered. That is one of the main benefits of getting an arc flash study done. Of course, for compliance of arc flash, coordination, equipment ratings, and all that wonderful stuff that we talked about needing every 5 years at a minimum. Arc flash studies, by and large, will include most everything that you need, including those one-line diagrams. Example being the type that we showed just a little bit ago. Okay, and also a side note, there's training with every study, because knowing what to look for on those diagrams and how to read the information and utilize those labels and everything, that doesn't happen just automatically. People have to get familiar with it. They have to be given the chance to learn about it. And so we feel, these studies are great as long as you know how to use it. That's why we include free training with each of them. Okay, so this topic, I feel like we are wrapping up a little bit sooner than usual, but I am open to any questions, concerns, follow-up to this topic. We can always go through even your specific diagrams and talk through, okay, what could be improved? How could you utilize this information, or talk about coordination or arc flash studies or short circuit calculations or whatever you need. We can always help with that as well. Understanding what's required and why is, of course, the first step to achieving compliance, and more importantly, safety. So I'm going to open it up for any following up of Q's and A's, so questions and answer time. If you want to go ahead and hop off here, no problem. We can always touch base later. You can call the office, ask for Caitlyn. I'm the only Caitlyn here, so there you go. They'll know who to talk to, or you can email me directly, cwininger@herzigengineering.com. Thank you so much for your attendance today. It was was a good amount of interaction. That always makes it really nice to have lots of questions and comments and feedback that yes, you're listening and paying attention and curious, and that way we can make it useful for you guys as well. So once again, I'll open it up for any questions that may come up. Otherwise, thank you so much and continue going home safely there. All right, got another question here. Use this information to review, determine how much change for renovations, where that our drawings have not been fully updated to reflect new connections. Last study was more than 11 years ago. Yeah, see that is long enough that we would typically say just recollect it. If you have one-line diagrams to work with, fine, but most of the time, I mean, 11 years is a long time to go without updates. And I can bet that there's a lot of things that have changed, especially if you've got new connections, new connections to switch gears and transformers. That's going to have a huge impact to your study. Another question. So at one point we mentioned offering possibility of train the trainer class for 70E. So we do have train the trainer for like our 4-hour electrical safety training based on the NFPA 70E. It's typically like a 2-day endeavor where I would sit down and explain all the details behind it and all the frequently asked questions and give you the tools to answer them. As far as going through cover to cover of the 70E, it is still something that we could definitely do. I feel confident that we could do that. It would probably be more than 2 days. Nothing specifically has been developed, but if you're looking to just go cover to cover, we just buy books of the 70E and we talk about it. So if you're interested in that, we can always talk more. Just reach out, send us an email, call the office, whatever, and we can figure out what you're needing. Okay, so for the train the trainer for the 4-hour class, we schedule it on an as needed basis. We don't like to have too large of a class for that because part of that train the trainer course is allowing you to give the training back to me, and I get to be the audience and ask questions and give feedback. And if there's too many people in the class, you don't get enough time to actually go through the material yourself. So we try to keep it pretty small and then schedule it on an as needed basis. That way you get the most out of it. Question, is it virtual? It can be. I haven't typically done that in the past, but I don't see any reason why not, because it's, slides and presentation, and if you know how to share a screen on Zoom or Teams, I can follow along. When you're making changes on the fly to your one-line drawing, at what point is a new engineer stamp required? Kelsey, fantastic question. So for creating the one-line diagram, not necessarily. However, if you use that to perform a calculation, so if you rerun those calculations, then an engineer needs to review it and stamp on that drawing or the report specifically. Because on one hand, if you're just documenting what's physically there, that's one thing. If you're using that information for a study, that's an engineering stamp required. Thanks, Mike. All right, guys, thank you. I'm gonna disappear into the background unless anything pops up. Have a great day.